Thermochemistry 5 is about the energy of phase changes. Let's look at a heating curve for water. A heating curve shows the energy changes that occur during phase changes, and they can be quantified by using a heating or cooling curve. So we're going to be talking about the heating curve for water throughout this entire video. Here is the heating curve, and it is broken into segments. I'm going to look at each segment individually. So let's start with the segment A to B. In segment A to B, as heat is added, the temperature of ice increases. Now, throughout this video, during these segments where we see the temperature increasing linearly, I'm going to ask you to consider the slope of the line. So we're going to compare the slopes throughout this video during these particular segments where there is an increase. The slope depends on the mass and the specific heat capacity. And in this case, we're dealing with water. Okay, so we're going to look now at A to B, and we're going to talk about what's occurring during this particular phase where water is ice. In its ice form, we have the molecules. Now, recall that the molecules are vibrating, but they cannot move relative to each other. In other words, they are unable to change places. They're unable to slip by each other. They're simply vibrating. However, as the temperature of the ice increases, water molecules in the structure are absorbing heat energy and begin to vibrate more vigorously. So as heat continues to be put into the system, these molecules continue to vibrate more and more. Ice has a specific heat capacity of 2.09 joules per gram degree Celsius. Now that is different than what we've looked at for liquid water. So it's important to understand that the different phase changes for the chemicals, and in this case water, have different specific heat capacities. Very important point there to be made. During segments where we see this linear increase of temperature as a function of time, you will be using Q equals MC delta T. Now, in Thermochemistry 6, we're going to apply everything I'm going to discuss in Thermochem 5, but we're going to look at it mathematically. This is more of a conceptual podcast. So during these segments where it's heating up, you will be using Q equals MC delta T. Now, the next segment is B to C. Molecules during this segment now have enough kinetic energy to start to overcome attractive forces. Let's identify attractive forces. These are intermolecular forces occurring between and among molecules of water. All right, so now that there's enough kinetic energy, they're able to begin to move with respect of one another, to basically slide by each other. So again, let's look here at this, at our molecules in the liquid state are able to slide past one another. Recall, in the solid state of ice, they could only vibrate, but were unable to slide or move with respect to one another. So that's a big distinction. The next point to be made during this curve is there's no increase in temperature occurring. As more heat is added, the temperature of the system remains constant. It does not change. It stays at 0 degrees Celsius, and this will be the case until all of the ice has melted. So this is dependent on the amount of the ice. Again, we're going to stay at a constant 0 degrees Celsius, which is at the melting point for ice. Let's look at the intermolecular forces. The predominant intermolecular force here being hydrogen bonds that are occurring among these molecules. We know hydrogen bonds are strong intermolecular forces. So it takes a lot of energy to be put into the system to break these intermolecular forces that exist. So during this portion of a heating curve where the slope equals 0, i.e. the temperature remains constant, what's occurring? Intermolecular forces are being broken. So from A to B, we had a heated up section. B to C is a break it up. Heat it up, break it up. So we heat it, we reach this temperature, this threshold where the water molecules can begin to slide relative to each other and slip past each other. This is the melting, and the constant temperature of 0 will stay the same until the entire sample is melted into a liquid form. This is called the heat of fusion, or enthalpy of fusion, often denoted with the subscript FUS for fusion. It is defined as the quantity of heat required to change a particular quantity of a pure solid at its melting point into a liquid. The heat or enthalpy of fusion. The enthalpy of fusion for water is 6.0 kilojoules per mole. Q, or the amount of heat in joules, is known, or can be calculated rather, by taking the enthalpy of fusion and multiplying it by the molar quantity, denoted in this case with a lowercase n. You may also see this denoted other ways, but lowercase n is the most the common way of expressing moles when dealing with molar quantities and enthalpy changes. So if you look at this mathematically, what it will give you, if you multiply a quantity of kilojoules per mole and you multiply that by the molar amount, well, moles will cancel out. Okay, so if moles cancel out, what does that leave you with? Energy in kilojoules. And if we are calculating heat, lowercase q, don't forget we're going to need to convert that over into joules, where we end with our units of 6,000 joules. So the enthalpy of fusion is 6.0 kilojoules per mole, or 6,000 joules per mole, and the amount of heat required, 6,000 joules. These are quantities that you're going to need to remember, because it's very easy when solving these problems mathematically to use the wrong specific heat capacity or to use the incorrect enthalpy value. So enthalpy of fusion can also be expressed in terms of grams. Remember, its definition is per amount. So this amount of 6.0 kilojoules per mole is equivalent to the enthalpy of fusion reported as 0.333 kilojoules per gram. Now, where did that amount come from? By taking 6 and dividing it by the molar mass of water, which is 18 grams per mole, and that will convert into kilojoules per gram. Go ahead and pause the video and try it yourself. Take 6 divided by 18. That's where 0.3 repeating comes from. Be ready for both of these values. Be able to readily convert between the two if needed. Now we can talk about our next segment, C to D. It's another heated up segment where we see the slope of the line increase as a function of temperature. It's a linear increase, but please note that this increase is at a slower rate. In other words, the slope of this segment is less than the slope of segment AB. This is because the specific heat capacity of water in its liquid form is greater than ice. All right, so we have ice reported as 2.09. We saw that in the last example, compared to water, which is 4.18 joules per gram degree Celsius. And in many of our previous computations, we've used 4.184 joules per gram degree Celsius. We're not going to worry too much about that extra digit here. So here they're being reported with three significant figures. We see the water molecules in this animation are now beginning to move even more so relative to one another as heat energy is put into the system. Okay, so C to D is a heated up segment. And what are we using when we do heated up? Recall, heated up is Q equals MC delta T. So for this segment, we can quantify it by using the mass of the substance, the specific heat capacity of liquid water, and the T final minus T initial or delta temperature. All right, so during segment D to E, we now have a break it up segment. This is where water begins to boil and the temperature is going to remain constant. We have a slope of 0. It's going to stay at 100 degrees Celsius until all of the water, all of that given quantity, that amount has been converted into steam. Okay, so first thing you may notice is relative to the other segment where we were breaking it up, where we had the enthalpy of fusion. This segment takes a lot of energy compared to the other segment from B to C. D to E requires a lot of energy. Now, the reason for this is all intermolecular forces now are being completely overcome by the end of this phase. By the end of this phase change, all of the hydrogen bonds and London dispersion forces, all of these intermolecular forces are completely overcome. For this to occur, it requires a tremendous amount of energy input. So now it is time to define the enthalpy of vaporization. The enthalpy or heat of vaporization is denoted with a subscript VAP for vaporization. It's the quantity of heat that is required to change a particular amount of a pure liquid, in this case water, at its boiling point, in this case 100 degrees Celsius, into a gas or steam. The enthalpy of vaporization for water is 40.5 kilojoules per mole. The heat that is required is going to be obtained by multiplying the enthalpy of vaporization by the amount in moles. That's the lowercase n. We can perform this computation using dimensional analysis. We can convert our molar quantities dividing by the mole. Then we can go and change kilojoules into joules, which will complete the conversion using dimensional analysis. Now we are left with the units of joules, and we can express it in this amount of joules. Now, if we look at this in terms of the change in enthalpy, we have 40.5 kilojoules per mole. Now let's multiply that by the amount, the molar mass. And in this case here, when we multiply by the molar mass, which for water is approximately 18 grams per 1 mole, we can cancel out the moles, and now we have a value of the delta H, or change in enthalpy of vaporization, expressed in terms of a gram. That number is 2.25 kilojoules per gram. Okay, so two different ways to express the heat of vaporization. You'll need to be able to convert between both of these readily as needed. Okay, now we can look at segment E to F. Segment E to F is where the water temperature again begins to rise. So this is another heated up segment. But notice it's occurring at a faster rate than the other two segments. In other words, the slope of this line is greater than both of the other slopes. Slope 1 was where we were heating up ice. Slope 2 was where we were heating up water. Slope 3, from E to F in this case, is where we are now heating up the steam. This is due to the specific heat capacity of the steam compared to ice and water. You know it's going to be lower, and because it's lower, it results in the fact that the rate of the heat of increase is greater here than what we saw for ice and for water at 2.01. So one point that's important to make here is we've looked at heating curves throughout this video, but the reverse processes can also be studied, and those are called intuitively cooling curves. So during this segment, as we have for the other heated up, we're using Q equals MC delta T, given the mass of the substance, the specific heat capacity of the steam, and then the change in temperature. In the flat segments, we were using the enthalpy of fusion and the enthalpy of vaporization, where there was no change in the overall temperature. So a heated up, break it up, heated up, break it up, and now heated up segment. In this video, we went through the conceptual and intuition behind a heating curve, specifically looking at water going from a solid to a liquid to a gas. We have a lab that we're going to be conducting to investigate these changes in physical processes in this case, and we're going to be able, as a result of that, to generate a heating curve as evidence that energy has been put into the system, resulting in a breaking up of all intermolecular forces throughout the process, reaching the gas, which led to phase changes. I'll see you guys in class.